Hey, what's going on, everybody? I'm Carl. I am the presenter for this session, and I'm the author of the book Serverless Machine Learning in Action. This is what this session is actually going to be about, and in particular, I'll focus on a particular aspect of machine learning, which is commonly used in deep learning and artificial neural networks. So this session is going to be about what's known as automatic differentiation. Just a little bit in terms of my background. If you're interested, I encourage you just to Google my name, search for Carl Osipov. You'll find a lot of the information about what I've done. I worked as a software engineer, data scientist, technology executive for about 19 years at this point. I worked primarily at Google and IBM. And a lot of what I'm going to share with you today is really based on my experience with ML. So if you're interested, there's some links there on the slide. If you want to reach out, feel free to shoot me an email. That's the best email to contact me. If you prefer more of an anonymous way of reaching out, that's my Twitter handle right there. But that's pretty much it about me. I want to make this session all about this book that you're seeing there on the right-hand side. So the book is about serverless. So is it really about doing machine learning without servers? No. So serverless here means without using servers during your machine learning development experience. So if you're a machine learning practitioner, if you're a data scientist, if you are a machine learning engineer, you probably have been in a situation where you had to put your machine learning system up on a public cloud like AWS, GCP, Azure, and then you were stuck spending a lot of time figuring out different services in public cloud, figuring out how to maybe get something like Spark up and running in cloud, properly configured. So, it takes quite a bit of effort. So this book is all about minimizing all this overhead, all of this operations busy work for a machine learning practitioner, and instead helping you stay productive and helping you work on what you do best, which is ML. So obviously in this short session, which is going to be just probably about 90 minutes or so, we're not going to be able to cover everything. So if you're interested in the scope, just navigate to that bit.ly link. And if you want to check out the whole book, you can use the discount code on the bottom right. So that's the best way to find out what's in the book in the entirety. But in this session, I'm going to focus on this PyTorch automatic differentiation feature known as AutoGrad. So if you have done machine learning before today, you may have heard about PyTorch. So PyTorch at this point is what I think is the leading machine learning framework for doing neural networks. You may have heard of TensorFlow. Well, at this point, PyTorch is leading by many indicators. And PyTorch is used for deep learning in companies like Tesla. So for example, they're using PyTorch for the Tesla automated driving capability. And PyTorch is even used for research. So top research organizations like OpenAI are using PyTorch to create cutting edge language models. So a very, very powerful framework. I've used TensorFlow in the past. I switched over to PyTorch, and I'm not looking back. Now, there's a specific feature within PyTorch known as AutoGrad. And AutoGrad is all about providing this ability, which is critical for neural networks, to backpropagate gradients. So what does that mean? Well, this is what this session is all about. I'll teach you what that means exactly from first principles. And in fact, by the end of the session, you'll be able to implement automatic differentiation using basic Python on your own. In fact, I'll provide you with a notebook on how you can do that. So that's what the session is all about. Let me go ahead and get started because we're about 5 minutes into the intros. And let me fire up my Colab environment. So if you've never seen this before, which I doubt because most of you I think are Python developers, this is the Jupyter Notebook environment available from Google, and I'm pulling up an existing notebook that actually I linked to in the running chevron in the lower third. So if you want to follow along, feel free to open up that link. There are two notebooks there. There's the exercise notebook, which I copied into my environment, and that's what you're seeing on the screen. But in addition to that, there's also a solution notebook with all the code already in there. So what I'm going to do is just live code for this exercise notebook, explaining as I'm going along with everything that I'm doing. So just to give you a little bit of a background in terms of what's going to happen in this notebook, I'll introduce very quickly this core data structure known as a tensor. So it's core to deep learning, and it's very fundamental to many areas of machine learning. So I'll explain quickly what is a tensor. And fundamentally, it's a multi-dimensional array. But in this session, we'll stick primarily to two types of tensors known as scalars. Think of them as individual values, and arrays, or think of them as Python lists if you prefer. So I'll show you how you can use PyTorch to do basic operations on tensors, and use this PyTorch autograd framework for linear regression. Now, I've talked to many machine learning practitioners who've seen this PyTorch autograd framework, and they just use it as is. So they don't really understand what's going on behind the scenes, and it can be tough to figure out how to use it appropriately and figure out all the details of the framework. So what I'm going to do is show you how you can solve a very fundamental machine learning problem, data science problem, which is linear regression using PyTorch. I'll explain what are the common questions that come up when people try to use this automatic differentiation feature for linear regression and for other models, and then I'll dive into the behind the scenes picture and explain how you can actually implement key features of automatic differentiation using Python yourself. So once we do that, I'll be able to explain some of the design principles behind PyTorch, help you understand why autogradient, this autogradient autodiff framework works the way it does. And by the end of the session, you'll be a lot more comfortable understanding how to use this backpropagation automatic differentiation feature from PyTorch in your own code. Now, in the chat, I'm getting a request to get linked to the notebook. Let me do the following. I'll actually go in and type in the bit.ly link to the notebook into the chat. And maybe if somebody can help me out and type in some of those other links into the chat as well, that'd be awesome, because the links are actually running in that lower third on the bottom of the screen. All right, so that's what we're going to do. This should take us another hour and 20 minutes or so. So if you're interested, feel free to join in, and let's get started. So what I have here right now is just a bunch of steps to go ahead and import some of the prerequisite libraries. So if you've ever done any kind of data science or machine learning in Python before today, a lot of this should look familiar, but fundamentally, here's what I'm doing. I'm importing the PyTorch library, so I already have it pre-installed here, and I'm aliasing it as PT. So you may have seen some people use alias torch instead, but PT is easier on my fingers when I type it, so that's what I'll stick to. And these next two lines, 2 and 3, are basically importing a graphing library. I'll use it very briefly just to illustrate the problem. But we're not going to do a lot of visualization. It'll basically help us generate scatter graphs and some basic line plots. So this line 4 is actually setting the figure size so we can get an easy to read figure. pt.manual seed. So this is actually a PyTorch feature where you specify the seed for the pseudo-random number generator. So if you generated pseudo-random numbers in the past, should be familiar. And then finally, this dunder method version reports that I'm using PyTorch version 1.5.1, and this is the CUDA enabled version. So this means that you can actually accelerate PyTorch using GPUs. Now, in this session, I'm not going to be using GPUs, but all the concepts that you learn here today apply to GPUs as well. So let's recap this idea of a tensor. So if you've ever used arrays and arrays of arrays to represent a matrix, you're like well on your way to understanding tensors. So tensor is what's known as a multi-dimensional array, or it's a general point of view on what is an array. If you used ND arrays and NumPys, in NumPy. This is pretty much the same thing with a few exceptions. So I'm not talking about tensors that exist in physics or tensors in some of the more abstract parts of mathematics. This is tensor for deep learning, and it's a multidimensional array. So when we have this kind of a multidimensional array, the key description of this array is the number of indices that you need to actually access the value in a tensor. So let's actually break this down and figure out what's going on. Well, the most obvious kind of a tensor is essentially a list or an array, and this is what's known as a one-dimensional or rank 1 tensor for short. So what this means is that you only need a single index value to pull out some value stored inside of this array. So it might be kind of a weird way of looking at Python lists for you, but keep in mind that you just need a single index value to pull out a value from this list data structure. So that's rank 1 tensor. And then if you've ever built matrices where you have arrays of arrays, right? You can have one set of arrays for the rows, and then the columns are basically represented as arrays of arrays. Well, you need 2 indices to pull out a value from that kind of a data structure, which means you have rank 2 or 2-dimensional tensor, and that's what we call a matrix. And the cool thing about tensors, and this is what we'll do in this session as well, is that you can go in the other direction. So you can imagine having a rank 0 tensor, and if you think about it for a second, basically it means you don't need any indices at all to get a value out of a tensor. So what kind of a data structure is that? Well, obviously that's just a variable, right? What kind of a data structure does not require an index in a programming language? Just a variable, or as we'll call it in this session, a scalar. So scalar is a term that comes in from mathematics. And the cool thing about tensors, and if you do advanced deep learning, you actually do this in practice, you can actually go on further. So you can go into rank 3 tensors. And if you've ever stored graphical images, think like color images, right? You can have a color images that has the channel dimension. So it has something like red, green, blue, and alpha channel for opacity. So that would be an example of this dimension. Like think of it as a depth of this rank 3 tensor. So that's the channel dimension. And then the image itself is actually stored as a matrix of x, y values of different pixel intensity. So intensity of the red pixel, intensity of the green pixel, and so forth. So it's a highly general data structure, data container, if you want to think of it that way, and it's very useful in deep learning. The last thing I want to mention about tensors, and this is important if you're actually planning to use tensors as a machine learning practitioner, is that along every dimension, you have the constant number of elements. So this means that, for example, if you have a rank 2 tensor, you must have the same number of elements along every row. So it's not like you can have 50 elements in the first row and then 25 in the second row. It doesn't work that way. So it's always the constant number of elements along every dimension. So in a short, that's the tensor. If you want to learn more about them, check out the book. So let's actually switch over to live coding. I'll do a quick check on the chat messages. Looks like some of you got the links, which is awesome. So let's actually go ahead and play around with some tensors. And what I'll do here is that to initialize this X as a tensor array, I'll use the PyTorch APIs, and in particular, I'll use this PyTorch API called linspace. So if you've ever used NumPy linspace, hey, it's exactly the same thing. And what I'll do is that I'll initialize it with 50 elements between -5 and 5. And actually, let's take a look at these elements. So here's what it looks like. I know it says tensor. If you use NumPy, it says array. But this is what's known as a one-dimensional or rank 1 tensor. Right? You only need a single index to fetch a value like that. Okay, so that's X. And if you have some machine learning background, the idea with all these values that we just generated is to set up a linear regression model, which means that we need some data that, let's say, exists in 2 dimensions. So we'll have a linear regression model in 2 dimensions, which means that we have 1 dimension for the features, which is going to be uppercase X. And then you have Y. And Y we're going to define as 2 times X. If you're wondering about the period, that means that I want to use the floating point number value. And here, in order to generate some noise, I'll use the built-in PyTorch function called rand_n, which is basically using Gaussian distribution. And for the size of this rand_n, I'll create this tensor of noise of the same size as x, meaning that I'll take every value from x, right? So that's our input tensor, I'll double it, and then to every value, I'll add some of this Gaussian noise. So if you remember the shape of the that bell-shaped standard normal curve, this is the kind of noise that I'm adding there. And this is why these values are not exactly double what they are of x. So in fact, what I'm going to do is I'm going to go ahead and plot this as a scatter plot. So let's plot it this way. And in fact, what I'll do alongside of that is that I'll plot x and twice x without noise. So you can actually see what this diagram should look like. So in fact, let's change this a little bit. Let's change this to a plot. So, and now you can see that the dots that are in the x and y values, right? So along the horizontal axis, we have the x, and the y represents the vertical axis. So the blue dots are the data points that we just created, and the red line is just the plot of twice of x, right, without the noise. So why do this, right? Obviously, you can do this in any language. This is not too interesting. So let's actually transition over into using PyTorch, and I'll show you how you can solve this classical linear regression problem using the gradient descent algorithm, which is used to train neural networks. So essentially, we're going to transition here from regular data science into some aspects of machine learning and deep learning. So here's what I'm going to do. I'm going to start introducing some of these features of the PyTorch AutoGrad library. And to do that, I'll create a model parameter. So why do we have this model parameter? The problem that I want to solve is essentially estimating the slope of this red line, okay? And the way that I'm going to estimate it is by using the data, using these blue dots, okay? So I'm going to feed in the blue dots into my linear regression solver, right, or estimator, which is going to use gradient descent. And I'm going to try to recover the shape of this trend between the values, the uppercase x and the y. So ideally, I should be able to recover this value of the slope of this trend line that you're looking at. And the way that we're going to do this is traditional way that we use in machine learning, which is to build a model. And our model in this case is going to be super simple, just one single parameter. We're going to call it W. And I'm going to initialize it using what's known as a torch empty method. I'm just going to say, hey, give me a single scalar. So here, this is the size. And if you take a look at the resulting tensor, it's a scalar. Now, if you call pt.empty, right, it gives you some value, some initialized value. In this case, we got lucky. It's pretty close to a 0. But I want to be more certain. So what I'd like to do is actually take this W and initialize it using a random value. And for that, I'll use pt. Actually, let's use this initialization function called uniform. So if you've ever seen this flat uniform distribution from -1 to 1, that's exactly what I'm using. So let me parse this out. This means go ahead and use the uniform distribution from -1 to 1 to initialize the value of the model parameter W and shove the result into W. Actually, let's do it this way. Make things easier. There we go. So now it will complain about the deprecation because I'm using an older uniform initialization. But now you can see that the value that we initialized the model to is this random value from the range of -1 to 1. And if you're wondering about the pseudo-random values, basically means that any value in this range is equally likely. That's what having a uniform distribution means. Okay, so that's W. And if you're wondering, if you're more of an expert in deep learning, you're wondering why I'm not using better initialization like Xavier or K-means initialization, it's because this is just a single parameter. I just don't have any additional inputs or outputs for this parameter to use more complex initializations. Now, the whole point of having this W value is that now I can actually use this to help me make guesses based on the data. So what does it mean to make guesses? Well, in machine learning, we have this concept of a forward function, which makes guesses about the data using the model. So our model is super simple. So let's go ahead and explain how we're going to make guesses about what is the predicted value of y. So we're going to say that this model is going to generate predictions of y simply by taking x and multiplying them by w. And then we'll return the predictions. This is all that this model is going to do. So we take the input data, remember these are horizontal axis values along the x-axis, multiply them by a single model parameter that generates some predictions, and then we return those predictions. So just if you wanted to see what the example would look like, it would be forward of x, then w, and here are predictions. Well, obviously these predictions are terrible, right? If you think about the original values that we generated here, you can actually see them. For example, the first value for y, what we say is the right value. It's -8. It's way off the prediction. But that's the whole idea behind machine learning, right? We have a way to model data, we make an initial guess, and then we improve that guess over time. So that's the approach that we're going to take here. So let's go ahead and do that. And then the question is, how do we estimate how well we're doing with guessing? Well, in order to do that, we need to be able to define what's known as a loss function, or if you prefer, cost function. So let's call it MSC for mean squared error. And this is going to measure how well we're predicting. And the way that it's going to measure is that first it'll estimate the error, and the error is simply going to be the difference between the predicted and the actual values. And then what we're going to return is the mean of the squared differences, so mean errors. So let's go ahead and return pt.mean error squared, right? So that's exponentiation in Python, and we're returning the mean squared. So this means that we can actually do things like MSC, take the actual values, right, from our data set, and then compare that to the predictions of the model based on the input data and the model that we're using, and return our error. And that's it. So this is actually the mean squared error based on the current versions of the model. Okay, so that's where we are. Now let's actually go ahead and start using gradient descent. So everything that you've seen so far is just basic definition from machine learning. There are different ways of solving this problem. How do you actually minimize loss, right? How do you reduce the loss of this function by changing w? There are different techniques for solving that. But the technique that we're going to use is gradient descent, because it makes use of the PyTorch autodiff feature. And it's a very fundamental algorithm that you need to know if you ever want to get into neural networks. Now, in my implementation of gradient descent, I'm going to use this definition of epochs and learning rate. So these are constants. So if you're wondering how I got them, the answer is, the simple answer is trial and error. The more sophisticated answer is hyperparameter tuning. So if you're interested, happy to talk later about hyperparameter tuning, but for the time being, let's just say that these constants can be used to solve the problem. But what we really care about is solving the problem, not necessarily these constants. So the way that gradient descent is going to work is that we take a bunch of gradient descent steps. So what does this mean? Let's actually do, actually arrange epochs. Let's do these epochs of gradient descent. And here epoch means that we are actually iterating for the entire data set, entire training data set, to improve our model, to create our model. All right, so let's go ahead and implement it. The first thing that we need to do is figure out our predictions and measure the loss on those predictions. So what are our predictions? We're going to call them ypred. And remember that we do a forward method. We take x, w is our model, right? A simple model with just one parameter. So these are our predictions. And our loss is what we define using mean squared error as the difference between the actual values and the predictions. So that's it, right? So that's our loss. Nothing too complex so far. What makes this different is that notice that now we're actually doing this repeatedly. In the past, I showed you that you can compute these guesses, right? Guesses for y or predictions for y, just one at a time. But what we're going to do now is do these in epochs, right? In these complete passes over the data set. So in order to do that in context of gradient descent, here you need to start using something that actually has to do with the PyTorch autodiff library. The first thing that you need to do is make sure that W is actually initialized with gradients. So this is the first kind of feature that I need to add here, which you may say feels a little bit magical. So let me go ahead and change this in the code, and then I'll explain what happens. Notice that now, when I'm creating this tensor, let me go ahead and reinitialize it. It has this feature that says requires grad equals true. Now, I'm going to give you an introduction answer as to why I'm doing this, and then I'll do a deeper dive behind autodiff and actually explain in code how you can actually implement this grad on your own. At a very, very high level, what this means is that if you have a tensor, like in this case, it's a simple rank 0 a scalar tensor, requires grad equals true, ensures that you can actually compute gradients or derivatives in this case for the values of this tensor. So if you're not sure about the difference between derivatives and gradients, I'm sure you know about derivatives from college, but gradients, think of gradients as multidimensional derivatives. So if you compute derivatives across more than one variable, that's basically called a gradient. So this means that we can compute gradients for this value of the tensor. So if you're feeling unsatisfied from this explanation, don't be surprised, because the first time I saw that, I wasn't very happy with that explanation either. This is what this session is all about, teaching you what does this actually mean and how do you actually take advantage of this. Okay, so that's the first change that we've made, right? We redefined W to actually have this gradient feature. So what this means is that now that you have this gradient feature, the first thing you need to do is what's known as zero out this gradient. Now, this is the step that actually seems most magical to users of PyTorch. And probably one of the most frequent questions that I get is this zeroing out of the gradients. Do I need to do this here? Can I put the zeroing out of the gradients here? Can it happen after backward or before backward? The short answer is hang on. We'll dive a little bit deeper to explain what this gradient thing is. Why do you need to zero it out? And then you'll be able to figure out on your own where exactly it needs to happen in the implementation of your gradient descent. Now, the second step, which is loss that backward. At a very high level, again, this introductory answer. This is actually doing back propagation of mean squared error back to this parameter, back to the model parameter. So it's figuring out how to change what is the gradient of W with respect to the loss. Or in other words, how do the changes of the W parameter impact the changes in the loss? Because remember, the idea is to minimize this loss. Minimizing the loss means improving the predictions that you're making with this very, very simple model. So these are your predictions. This computes the loss, the difference between the predictions and the actual values. And the idea is to improve on the loss. So how do you do that? If you've done gradient descent before today, you know that the approach is to take your model parameter and you can actually change the data, in other words, that value in the tensor, and reduce it by the learning rate times w.grad. So that's all. And in fact, if I go in and run this, assuming I didn't make any bugs while I was chatting, yeah, so you can see that this worked, right? So it ran for 100 epochs, which means 100 passes for this entire data set of 50 points. And then at every step, it was actually changing the original value of the tensor. Remember, we started out with the value that was about 0.8. And now it's basically 2, right? That's the value that we use to generate the data set. So if this feels a little bit magical to you, I encourage you to go to Machine Learning 101, or if you're interested in the appendix of my book, I do an explanation of the intuition behind gradient descent. But conceptually, this should make sense, right? We're making guesses about W. We're figuring out how would changing W improve your predictions, or in other words, minimize loss. And we're changing W value in the direction to improve the prediction. So the w.grad is basically the kind of a change that you can make to W to improve the predictions. And if you've ever done linear algebra, you may have seen this kind of a solution, which is the analytical solution to linear regression. In fact, in PyTorch, of course, what you can do is figure this out on your own. So x.t is basically the linear algebra of operation of matrix transpose. So if I do this, it's essentially this left part in the parentheses. And then I need to raise that to the negative first power. So let's do inversion of this stuff. So here's what I get if I compute this first part of the analytical solution to the linear regression problem. And then I also need to multiply that by x transpose matrix multiply y. So that's the right-hand side of this problem. And now what I can do is multiply them together. Now notice that in this case, I'm dealing with scalars. So these are not matrices anymore. So I cannot use matrix multiplication, which is the @ sign, to multiply these two. I have to use just a regular multiplication. But basically, if I apply this ordinary least squares solution to the original problem, right? Remember, we started out with this data set. Our data set of x's and y's is represented by these blue dots. And the idea was to recover the trend between them. Sort of the statistics 101, right? Linear regression. And we've just done this 2 ways. One way using gradient descent, another way using this analytical solution. And in both cases, the result is the same, meaning that we can basically recover that underlying pattern in the data. If you're wondering, like, why am I going crazy with gradient descent? Why do I need all these iterations? The short answer is that if you look at the analytical solution, this is actually relying on a very computationally expensive operation known as matrix inversion. So if you have a data set that has a huge number of features, so think on the order of tens of millions, billions of features, this matrix inversion is big O n 2.3, so somewhere in that range. A naive solution would be actually big O n cubed. So it's not feasible for large data sets. But the nice thing about gradient descent is that it's scalable. You can actually scale it to many features. You can scale it actually across many nodes in a computing cluster. And although it gives you an approximate answer, gradient descent works quite well for modern neural networks. So the bottom line is that both solutions did not exactly recover that value of 2. Remember, we said that we'll take x and multiply it by 2 as the slope, and then add some noise. Well, if you're wondering why this solution, even the analytical solution, did not return the value of 2, well, it's because that noise did not allow us to estimate the exact slope. We found an approximation, but that's the same thing that what the gradient descent approach gave us, right? Same idea. We're looking for estimate, for approximation. And in real data sets, you're going to have noise anyway. So running this computationally expensive, ordinary least squares approach is not really getting you a lot of benefit. So let's recap where we are. So we started out with a data set. Then we took that data set and ran it through this gradient descent algorithm for 100 epochs. Remember, 100 iterations or gradient descent, using the entire data set in this iteration. And basically at every iteration, we take our model, we make a guess about the whatever we're trying to predict, which is our y, using that model. We figure out how good the guess is compared to the actual values, and then we do these like quote unquote magical operations. We zero out the gradient, we compute the backward loss. So I think everything except these question mark lines of code, everything except 6 and 7 should sort of make sense. And I think line number 9 will make more sense after this next part of the presentation. So what we're going to do is actually dive deeper into what does it actually mean to zero out the gradients? Why do you need that? What do you actually do when you backpropagate gradients? What does it mean? How does this change our model? So let's go ahead and do that. And of course, if you have comments, questions, just have tons of ways of reaching me. I had my email there on the first slide, or if you want to post something in the chat, that works as well. Okay, so I showed you that you had to use this AutoGrad library, automatic gradient library from PyTorch, to use gradient descent. And behind the scenes, PyTorch AutoGrad is using an algorithm known as reverse mode accumulating automatic differentiation. So it's quite a mouthful, and I think it obfuscates what actually is going on, because this is a super important algorithm. In fact, I read a review of some of the top algorithms invented since 1970s, and this is one of it. And the cool thing about it, it was actually invented by a master's student in Finland. So the algorithm itself is simple, but it's extremely powerful because it's doing something known as chain rule from calculus. So if you've ever taken calculus and did chain rule by hand, this algorithm is actually doing very, very complex chain rule applications automatically. So there you go. Now, if you're new to automatic differentiation, you need to know that it's different from some of these other techniques. You probably know numeric differentiation from calculus. If you've ever done this approximation, if this brings back any painful memories where you take some function, like maybe a linear function, you add a little bit of this called epsilon, like a small step to it, then you find the difference between x plus epsilon and f of x, divide by epsilon, compute the limits. That's known as numeric differentiation. And while it works well in college textbooks, in practice, this is actually numerically unstable if you apply this directly to neural networks, for instance. And that basically happens because, as you know, the representation of floating point numbers is using this mixed point approximation, and essentially these floating point numbers don't actually give you exact results. And with the numeric differentiation, you accumulate a lot of errors if you try to use them directly. And this is also different. The automatic differentiation, or autodiff, is different from symbolic differentiation. So if you ever used packages like Mathematica, they have something called symbolic differentiation. So you can give them a function like y equals x squared, and it'll tell you, hey, the derivative of y equals x squared back to x is 2x. So that's great. It gives you an expression for the derivative. The problem is, computationally, symbolic differentiation is more expensive. So it does give you a very general symbolic expression for differentiation, but it does have quite a heavy cost, unlike autodiff. So autodiff is actually order of n, and n here represents the number of operations in your, basically in your loss function. If you apply autodiff to machine learning, it's order of operations in your loss calculations. And this generally holds when you have this loss calculation. So this means when you have a single output and many, many inputs. Okay, so here's the plan. I showed you the challenges with understanding the automatic differentiation feature of PyTorch. So there's a lot of this magical stuff that you've seen, like requires grad. You've seen the zeroing out of the gradients. It wasn't clear when to do this. You've seen the backward function. So what does that do exactly? I think the best way to explain automatic differentiation is to actually try to implement it yourself for a simple case. And the great thing about automatic differentiation is that it's super easy, in my mind at least, to implement it in Python. So let's go ahead and do that. Let's actually create this simple tensor, a scalar. And this tensor is going to have the following. So let's have this tensor, we're going to init it with a value. So we'll take a self and some value. And inside of that scalar, we're going to have the value of that scalar. And in addition to that, we're going to have a gradient. So this is where we're going to store the gradient, or the derivative of the scalar. And then I'm also going to introduce the backward function. So remember, the backward function is the one that actually computes the gradients, something like a loss function. And for the time being, in this default implementation, I'm going to make this a no-op. So this is going to be just a lambda none, okay? And this means, you know, if we call a backward function, it's just not going to do anything by default. Of course, that's going to change, but in the simple implementation, it's just a no-op. Now, let's implement the overrides for the Python add and multiply methods. So let's go ahead and implement addition of one scalar to another. So it's going to be a self and let's have it the other scalar. And then the result is straightforward, because the result is just a brand new scalar where we take the value of this scalar and then add to it the value of the other scalar. And then we return the result. That's it. So just take a moment to parse that out, and I think that should be fairly straightforward. Let's do the same thing for multiply. So if we're multiplying two scalars, we also have ourselves and some other value. Let's have a result. The result is going to be a brand new scalar, and the result is just a product of the self and the other scalar. So we need to return this. Let's actually do a sanity check just to make sure this works, because what we should be able to do at this point is create a scalar. Let's actually do this. Let's make sure that all our scalars are floats. And I'll later go with integer values for the time being. So let's create a scalar. Let's add 2 and 3. So let's have a scalar of 2 plus scalar of 3, and I expect that this works. It does, but the readability of the output is terrible. So let's change that. Let's actually create a more readable output. Let's create like a repr method. So it will give us a self, and let's return, I'm in Python 3, so let's return a formatted string that reports on the value and the gradient. Gradient is going to be self.grad. So for the time being, right, there's no gradient, right, because it's just 0. We're not doing any computation of derivatives. But you can see that we can do basic math. And in fact, this should already respect the precedence rules for addition and multiplication. So let's do something like 5. So if this works correctly, we get 17, right? Because 3 times 5, 15, plus 2, 17. So this works fine. I think this is enough for now. So let's just recap this. You got your scalar. Just take a moment to appreciate that, because in just a bit, I'll pull up my first trick where I'll use this class to successfully compute a derivative. You're probably looking at it like, Carl, how can this compute a derivative? Well, I didn't say it can compute any derivative. It can compute a very simple derivative. And here's how it's going to work. Let's create our x. And remember, AutoDiff computes derivatives at specific points of a function. So in this case, I'm going to use scalar 2. And guess what? That works. No surprise there. And I told you that I can compute derivatives. Well, I can compute it, but for this very trivial function, y equals x. So I want you to start putting your calculus hats on for a moment. Just think about this and think about what this looks like, right? So essentially, if you think about this function, it's that straight line going exactly through the center of the origin, y equals x. So this is what we're going to use to compute our first gradient or the first derivative in this session. So here's how you're going to do this. Remember that we're using floating point values, so that's cool. Let's do the first thing. Remember zeroing out the gradients? I said that that's important. Well, this is important because going forward, this will not always be the case. If you think about our scalar, by default, a brand new scalar always has x.grad equals 0. But remember that we actually want to run this in multiple epochs and multiple iterations of gradient descent. So this can actually change iteration to iteration. So this is one of the first reasons why we actually set it to 0. So, okay, so let's say it has to be 0. Now, here's the next thing that we're going to set. And that's going to be the y gradient. Okay? And this is probably where you're thinking, hey, this doesn't make a lot of sense. Like, why are we setting the y gradient, and why did you pick number 1 for the y gradient? We're trying to figure out how does changing x translate into changing the y, right? What's the relationship between them? We're trying to differentiate that function y equals x. So where did this number 1 come from? Well, if you think about it just conceptually, what we're saying is that y.grad is the rate of change that change in y has to itself. So this is basically, if you want to think of it in calculus terms, is dy dy. And what do you get if you divide something by itself? Well, that's a 1. So that's what we got to a value of 1 here. Okay, so hopefully you're buying into this so far. Now I'm actually going to go ahead and differentiate. So let's call our backwards method. So remember we said we're going to back propagate those gradients from y back to x. So that's what we're figuring out. So let's do that back propagation and confirm that after back propagating, the value of x gradient changed. So in other words, we're able to find out what is the derivative dy dx. And x.grad is actually storing that value. So notice we started with 0 and now x.grad is a 1. Okay? So here I want you to think about this for a moment, and if you're saying, hey Carl, that looks like cheating, I can see where you're coming from. The thing is, remember our definition of y? Y is just x. So when we said y.grad equals 1, we've basically overwritten this line of code. So we changed what is the value of x. So where's the magic? Well, I told you this implementation actually computes gradients for a very simple function. It does give you the right answer. If you have a function y equals x, this implementation works correctly. The backward is a no-op, but this does correctly compute the dy dx. So if this is unsatisfying, let's try a more complex example. You'll see that actually it's fairly straightforward to change this and get a more interesting function to work with and still get cool answers. So let's actually implement this backward support in the add function. Let's go back into our scalar. Remember our 13-line code scalar. And let's add part of the implementation that will allow us to compute back propagation of the gradient for more complex functions. So notice that when we are adding 2 scalars right now, we're not computing anything related to backprop. So let's change that. Let's do this. First of all, let's define what it means to compute the gradients. So define this backward function. In this backward function, actually what I'll do, I'll assign it to the resulting gradient. So notice that here I'm saying that the result of the backward function is the implementation of whatever backward function I'll put in here. So what is that implementation going to be? Well, we're adding 2 scalars. We need to backpropagate the gradients. Well, we need to be able to use the gradient of the result to set the gradient for self. Remember, this is going to be the resulting gradient. And we need to set the gradient for the self and for the other scalar, because that's what it means to send the gradient backwards, right? From the result back to whatever scalars were used as inputs to the result. And this is where the accumulating part of this algorithm comes in. So notice that if we're setting that result, what we need to be able to define is a scenario where both this scalar and this scalar are the same. So what we need to be able to do is accumulate these gradients, and that's exactly what's going on here. So plus or equals is the accumulating part for the gradients. And notice how we're going to define it. If you think about computation of the gradients, let's say you have a function that looks like this, right? So x is one scalar, z is another scalar, and you know that your y is going to have that gradient of 1, right? dy dy. We said it's going to have the value of 1. And we're asking, okay, what is the gradient dy dx? Again, here you need to think a little bit to calculus, and basically what this means, dy dx. This means that all things being equal, if you make a small change to x, how does this translate into a change to y? And the all things being equal part means that z doesn't change. Z stays the same. So any changes to x are translated directly into changes to y. Z is not carrying any changes at all. So what this means is that the gradient of the self vector, this vector, is just the same thing as the gradient of the output. So they're the same gradient. And the same thing is true for the other gradient. We want to accumulate, and then we just want to take the value from the result. Now, the last thing you have to do if you want to implement this kind of automatic differentiation is actually call backward recursively. Because what happens is that you can actually, you need to be able to combine many of these tensors together and send this backward computation, the sending of the gradient back across many, many scalars. So the way that you do this is just recursively call self.backward, and then you need to also be able to do this on the other scalar as well. So you call self.backward, other.backward, and that's it. That's all it takes. You know that the gradient is just the gradient of the result. Same thing here. So you've backpropagated the result to the two initial tensors that were used to compute the result. You called the backward recursively, which in a very simple case is just a no-op. You assigned the backward to the result, you returned it, and this is it. That's all that it takes to actually add backpropagation to a function that adds multiple scalars. So for example, let's start with a very simple example. Y equals x plus x. So if you think about this, again, think high school calculus, college calculus. This is y equals 2x. Same thing, right? We're just adding the addition here, using the addition to define the function. So that's all that it takes to define a function. And think about backpropagating gradients. Basically, you'll create a new tensor, right? Y is just this new scalar tensor that has two x's as inputs, and you want to backpropagate that y gradient to these input tensors, which just happen to be the same scalar. So let's say that this is scalar value 3. This is our y, and then let's run the backwards pass. And the backwards pass is exactly the same as before. So remember, zero out the gradient. Y gradient, remember it has to be 1. Let's use floating point numbers here. Let's go ahead and run the backward pass. So y.backward. So remember here, y.backward will run on the scalar that is produced by adding two of these x's together. And let's find out what we get. Well, here I can tell you it's not going to be 3. Because remember, the function that we're trying for is 2 times x. But I can tell you that now, if you compute this, you should get the value of 2, which is the case. So notice what happened here. You figured out how does the change backpropagate from y, because the change of 1 essentially was computed by respective changes to x's. So essentially, every small change in x gave twice the change to the y. And that's, you can keep expanding this. So let's change to y equals 3 times x, run the backpropagation, find out the gradient. No surprise there. You get dy dx equals 3. All right. So let's try to make this more complex. Let's see what it would take to actually do this kind of a backward propagation compute in the multiplication function. So let's do this. Let's take the scalar class that we just defined, copy and paste it into the multiplication function. And actually, what I'll do is move this around slightly so it's closer to the top of the class definition. And then let's go ahead and update the definition of the backward function for multiplication as well. So let's define the backward function. And let's not forget that in the result, this is the function that we should be using to compute the backpropagation. Now, the cool thing about this is that the logic is pretty much the same. So what is the gradient for the self scalar? So now this one that was used as part of the input to the result. Well, we know the gradient for the result, right? It's going in the opposite direction. It's going from y back to the x. So it's going to depend on the result. So result gradient has to be in there. But the thing is, here, if you think about the relationship between the x and the y, remember how I said that when you're computing the gradients, the question is dy dx, right? What is the relationship between the changes of y and changes to x? All other things being equal. Well, the other tensor just stays constant, right? If you're computing the change relative to x, the other tensor is just some constant. And that's exactly what we need to put in here. So in other words, the other tensor's value is that constant that multiplying the gradient. And that's how we're accumulating the gradient for the first input tensor, and the same thing for the second input tensor. Because in this case, the other tensor's value is the constant, and we multiply that by the resulting gradient. And finally, the last thing we need to do, so we don't forget how to backpropagate this, we need to call self.backward and other.backward, so we get that recursive call to backpropagate the gradients to the other tensors. That's pretty much it. So I'll leave this here for a moment, and then let's go ahead and run this. So here's our new implementation. Let's try it like we did before. Let's try it with a very simple scalar first. So let's say we have the scalar with a value of 4, and let's try a simple function where we just multiply x's 3 times like this. So we have x cubed, y equals x cubed. So what this means is that now if we run the backpropagation, so remember, initialize our gradients to 0, set the output gradient to 1, and then finally do the backpropagation. So let's do y backward. We'll backpropagate gradients to x and find out what x should be. So here, if you think about it, right, the gradient of x, since we have x cubed for the value of x equals 4, this means that we have 3x squared. So for value of 4, x squared is 16, and 3 times 16 gives you 48. So again, very simple implementation, something clearly obvious in terms of how we're getting this in the implementation of the backward function, but it gives you the exact value. And in fact, this scales to more complex functions because now we can do even things like plus x. So the entire function looks like y x cubed plus 2x. We can backpropagate that using the same code. And now, of course, the gradient gets updated to the right value because the analytical solution to this updated function, which is x cubed plus 2x, if you try to solve that analytically, you get 3x squared plus 2. So we already know that 3x squared gives you 48 plus 2 gives you 50. So that's the calculation of the gradient. All right, and now you basically have a working tensor, which is a rank 0 tensor, but it works. So let's actually, before the end of this session, take this implementation that we just created, this very, very simple implementation of AutoDiff, and apply it again to linear regression. So let's do the following. Let's again create a brand new model. Remember our random parameter. Let's initialize it to some random value. Remember, from -1 to 1. Again, I'll use that uniform. So a uniform method, passing w. We want the uniform probability between -1 and 1. Let's take a look at that w. So here's the PyTorch tensor. Remember, it still requires gradient. But instead of using that PyTorch tensor, what I want to explain is that we want to use the scalar for W. And now I can actually explain to you what this requires grad actually means. So by default, when you create tensors in PyTorch, they actually are missing that .grad attribute. Remember, in our scalar, we have a .grad. Well, guess what? If you have .grad, this basically doubles the amount of memory that you need to store for every scalar. You need to store the value, right? Remember the .val property, and then on top of that, you need to store .grad. So if you have a lot of tensors that have data in them, like for example, if you're loading up tensors of color images, like huge images, maybe tens of megs, and you're loading a collection with millions of them, that'll use up a lot of space. So that's why by default, PyTorch actually doesn't include this property with the gradient. And the only way to enable it in PyTorch is that when you create a brand new tensor, is that you need to set this requires grad true. But in our case, with our simple Python-based scalar implementation, we don't need to worry about it. We just create a scalar, and the way that we're going to create it is just by taking this random value, the negative 0.5964 that we just got, and we'll shove that directly into our scalar. So if you're wondering about these properties and methods, the .data is basically pulling in this data value, the floating point number, from the tensor, and item actually returns it back. So now we have the scalar with this randomly generated value, and let me actually shove it into that same variable W. So this is going to be our new model value. So now I'm going to actually create some linear regression data. So let's actually create data similar to the ones that we used before. So I'll create, in this case, a list of scalars. So let's say X now is going to be a list of scalars. And I'll create these scalars by doing Python range. So let's do I for I in range. Let's say it's going to be in the range from negative 50 to 50. And then what I'd like to do is actually let's multiply each one of them by 0.1. So we have 100 values that are in the increments of 0.1. So we'll use this as a feature values for the linear regression, right? So I'll just change this to slice the first few elements for readability. But now what you have here is some sample data that you can use for linear regression, except you're missing the y values. And for y, let's keep this simple without any noise this time if you want to. And I'll explain why shortly. But basically, let's create y by setting the values of x. So we'll use x sub I multiplied by 2. Remember, the slope for our line is 2. And this is going to be for I in range len of x. So basically iterating for every element of x, and every y is going to be twice x sub 1. Now, there's one thing that's a problem here. Notice that we're just doing this multiplication. We're not actually creating scalars. And for us to be able to do this linear regression, this simple tensors, we need to package them as scalars. So let's actually do that. So now x is a scalar. We need to make this a scalar so we can multiply correctly. So now we have scalar times a scalar. That's good. Let's confirm that's the case. We run this one. So we have scalars here, scalars in y. And now you have your data for linear regression. So let's see if this very, very simple implementation of AutoDiff in pure Python can actually solve linear regression. So again, let's go ahead and implement that function that gives us guesses. It computes the forward. So it takes the x and the w. Let's go ahead and do that guess. So how do we do that? We need to compute the error. How do we compute the error? Well, remember, we need to find the difference between the actual values and the predicted values. I'm sorry, let's do the predictions first. So the forward function is going to generate the predictions. How do we generate the predictions? It's going to be just x times w, right? So we take the W scalar, we multiply it by x sub I for I in range len of x, and that's what we return. So this forward function now gives us predictions for the inputs, and you can confirm that this works. You pass in the W and x, and you can see that this is giving you initial guesses off of that random W. Remember, we used that random value for W to generate these guesses. This is what they are. So the whole idea is to take these guesses, measure how good these guesses are using mean squared error, and then improve. So now we have all the tools that we need to do that, with the exception of the mean squared error calculation. So let's implement that function. So this function will take the our scalars for y and y predictions, and now we need to compute the error. So how do we compute the error? We need to take the y scalars and then find the difference between y and y predictions, right? And this is going to be for I in range len y, and these are going to have to be y sub prediction. This is y, and this gives you the calculation of the error with one exception. Remember that we never actually implemented the minus sign for our scalars. Let's actually go ahead and do that. So instead of just doing a minus, we can always do a plus, and then what we need to do is do a scalar, which is going to be -1 multiplied by the prediction. So this will give you the negative y prediction. We add that to y sub I, and this will give you the error. So that's the error. Let's find the mean squared error. So the mean squared error is two things, right? If we need to find the mean, that means that we need to be able to take 1 divided by number of elements in y. So this will give us the first scalar. Okay? And we need to multiply that by the sum of all the scalars that we have in the errors, right? We're finding the mean of this error squared. Now, one thing that I haven't done yet is actually square the error. So let's square the error. So let's do error I times error I, or I in range error. So SC is the squared error. And then finally, to compute the sum of these squared errors, let's do a sum of SC, and we need to give a starter value because it needs to be a scalar, right? We're going to try to add the first element here to a 0, but that 0 has to be a scalar of 0, so we can use a built-in Python function called sum. This will give us the sum of the squared errors. We multiply that by 1 divided over the number of errors. So if you prefer, we can do this. Sum of the errors. And this will give us the mean squared error, which actually is what we want to return. So let's go ahead and return that mean squared error, confirm that this works. So MSC of y, and let's do a predictions of these y's. Confirm. And it doesn't want to multiply something, so let's see. It doesn't want to multiply the x times the x sub I. Let me see which one it is. This is in the forward method. So the part that failed was in the forward, not anywhere else. So what we need to be able to pass in here is the correct implementation of the forward method. So the bug that I had is that I passed in y instead of w. So now if we pass in the w, these generate the guesses, the predictions for what the y's are. These are the actual values, and the MSC gives you our new homegrown implementation of a scalar tensor with the calculation of the value of the mean squared error. So that's pretty much it. Now, the only thing that we need is run that same gradient descent. So let's do that. Let's actually re-implement gradient descent using the approach that we've had before. So let's do same number of epochs, just so you can see it's doing pretty much the same thing for in range epochs. So gradient descent for epochs. We need to create the predictions. So forward of x and w. now we need to be able to compute our loss using those predictions. So let's compute the loss using the mean squared error function. There we go. And now we need to do all that same magic that we did before, except we're going to do it with our scalar class. So let's figure out what we're doing. So why are we setting the W grad to 0? So remember before you had to zero out the gradients? Well, now you should be able to say why you need this line of code. Remember, in your calculation of the backward function, you're going to accumulate gradients to W. So which means that every time you run this epoch, this iteration of gradient descent, the gradients are going to accumulate. They're going to keep adding into w.grad. But for every epoch of gradient descent, you need to compute the gradients from scratch. You need to find a brand new gradient because W is going to change, right? So that's why we're actually using this zeroing out of the gradient for our model. If you use PyTorch, in PyTorch, oftentimes you'll use an optimizer, zero grad, as the alternative to this, but it's doing exactly the same thing. Basically, optimizes zero grad, iterates for all the model parameters in your model that needs to be zeroed out, and is basically setting them to none, which is the PyTorch equivalent for gradient 0. Now, we also need to do the loss equals 1. So remember, this is our dy equals 1 idea. We're saying what the gradient of the output function should be. And of course, from the discussion earlier, you know it's 1 because it's the ratio of a change with itself. Well, in case of PyTorch, so in PyTorch, whenever you call the backward method, this actually sets the output gradient to 1 automatically. So sets 1 automatically. But you can change that. So in fact, if you look at the definition of the tensor backward method in PyTorch, it'll tell you that behind the scenes, you can change how to set the gradient for the output if you want to. This gets a little bit technical as to why would you want to do this. But if you want to change the output gradient, you can. Finally, remember that we need to actually run the backpropagation. So at this point, if you run loss backprop or loss backward, this actually runs this implementation of backward function that you've just seen moments ago for your very simple scalar. Of course, now the loss function is way more complex than any of those functions that we use, right? We're multiplying a lot of these data points together. We're computing the means, we're computing the squared errors, etc. So the function is a lot more complex in terms of the number of the gradients. But the computation for those gradients is super simple. It's like 4 lines of code for that self.grad and other.grad function. So now we've computed the gradients, which means that w.grad now has the gradient over our loss function. And this means that you can actually do the following. Let's go ahead and change the value of w by learning rate times w.grad. So we're taking a gradient descent step on w in the direction opposite of the gradient, which is the definition of gradient descent. And let's go ahead and run that and find out what we get back. So this is our gradient descent. And hey, no bugs. So this perfectly recovered the value that I just used to actually create the values of x and y. So if you recall, the initial data came in these scalars, just sampling the first 5 values out of each one of them. So these are the data values that our machine learning algorithm used, right? Gradient descent algorithm, and we perfectly recovered the slope that I set of 2 using gradient descent and using your scalar implementation. So that's pretty much it. And now you can say, hey, I know at which point in the loop to actually set the gradient to 0, because what if you set it to 0 here? Well, it doesn't really matter because you don't call the backward function up until this point. You want to call the gradient 0 in this case? Sure, why not? Doesn't really change things. Or, as many people actually do in practice, you can set the gradient to 0 after you update the value of the model. So in fact, in PyTorch, it's very common to do this step of the optimizer. So in PyTorch, this would be optimizer.step, and then call optimizer.zeroGrad to zero out the gradient. But of course, if you want to, there's nothing changing if you do the same operation in the beginning of the loop. In fact, they're equivalent, right? So hopefully this gives you a little bit of an insight into inner workings of automated differentiation. It's a super powerful algorithm, as I said earlier. It was called one of the top scientific computing algorithms invented since 1970s. I know that if you are going to be going to college in the next few years, it's probably going to be part of the curriculum. So definitely something you need to know about if you are planning on becoming a machine learning practitioner. But you can see that this is fairly straightforward to implement for simple functions like addition and multiplication. And of course, in PyTorch, what happens is that the PyTorch team implemented the automated differentiation not just for addition and multiplication, but also for more sophisticated functions like ReLU, for instance, rectified linear unit, which is commonly used in machine learning and others. So here, I'm going to stop, just going to type out a few more of these links into the chat. So some of these links I've already posted. So here's the link to the exercise that I just worked on. If you want a link to a solution, it's the this link, as I recall. There we go, AutoDiff solution. So both of these should work. The solution, of course, already has the code you need. And finally, if you want to follow some of the changes that I'm posting about machine learning stuff that I do, or if you're interested in getting a copy of this recording, what I'll do is actually post a link to the recording to the folks who sign up or check in using this form. So this is how I can actually get you information and send you a link to the recording. And that's pretty much it, pretty much everything I wanted to cover. So in this session, you've seen a lot. So if you've never used PyTorch, this is really a deep dive into what's going on with PyTorch behind the scenes. I showed you an example of a very simple tensor, a scalar, and then showed you how you can actually implement key features of automated differentiation for PyTorch yourself. And you've seen that if you implement it yourself, you can even do things like linear regression with this small implementation of your automatic differentiation algorithm. And this gives you insights into when and how you can use these PyTorch automatic differentiation app programming interfaces, and when and how you should use these operations like optimizer zeroGrad, optimizer step, and others, and why that sequence matters behind the scenes. So hopefully next time, if you're using PyTorch, or if you're planning on using the PyTorch code from my book, you're not guessing or you're not treating PyTorch AutoGrad as magic. Instead, you know exactly what's happening behind the scenes and how it's actually computing the chain rule of calculus for you using a fairly simple sequence of these kinds of recursive calls. So with that, what I'd like to do is say a huge thank you to all of you. I've posted up a link to the Serverless Machine Learning book. So if you want to learn more about PyTorch, more about how to actually use PyTorch as a machine learning practitioner, staying productive and developing your machine learning models without getting overwhelmed with concerns of putting your machine learning model into operations, babysitting your machine learning model when it's running in a cloud, definitely check out the book. You can learn a lot about preparing your data. You can learn about building machine learning models with PyTorch on AWS. And if you want to use the discount code there in the bottom right-hand corner, I'll post that as well. So the discount code that I listed is going to give you 40% off the list price of the book. So with that, again, huge thank you, and stay in touch. I gave you my contact information, and I wish you all the best in learning about data science, machine learning, and software development.